Hello, I'm Professor Bill Chaplin from the University of Birmingham, and today I'm going to be giving you a brief overview of the NASA TESS mission, which was launched just over 2 years ago. I'm a stellar astronomer, and now is a particularly exciting time to be able to study stars, since our ability to do that is being driven by a new generation of satellites and telescopes that are providing us with data of unrivaled quality on unprecedented numbers of stars. Stars are the building blocks of the galaxy. They drive its chemical evolution. And so by studying large numbers of individual stars, populations of stars, that tells us something about the evolution of the galaxy, its past, and also as well its future. But of course, studying stars on an individual basis is vitally important for informing our knowledge of stellar evolution theory. And of course, then the influence that stars have on their local environments, the fact that they act as safe harbors for planets and provide the energy needed to be able to give conditions that might support life on the surfaces of those planets. It's really this mission that really has revolutionized observational astrophysics for studies of stars and searching for planets around those stars, the NASA Kepler mission. Kepler was launched in 2009 with its prime objective to search for small terrestrial Earth-like planets orbiting sun-like stars. But also as well, it provided the data that enabled us to be able to study the stars themselves. And we were very, very lucky to be involved with the Kepler mission right from the outset, as I'll go on to explain. Kepler's main goal was detecting planets via the so-called transit method. So this is the very simple, elegant idea that if you're observing a star around which a planet is orbiting, and you're also observing the plane of the orbit of the planet edge on, there will be times during the orbit when the planet will pass in front of the star, it will transit the star, and if you're measuring the brightness of the star, you'll see a characteristic dimming, as shown here, which is called a transit. Of course, if you observe long enough, you'll see that transit come round again and again and again as the planet completes successive orbits of the star. So here one is detecting planets indirectly by the impact that the light has on the planet from the star. And Kepler has been tremendously successful in discovering literally thousands of planets orbiting sun-like stars, which are in our local solar neighborhood, the nearby parts of our galaxy. Now, because the planet is detected indirectly, in order to be able to say, for example, how large the planet is, also how massive the planet is as well, whether or not the planet might perhaps be orbiting in the habitable zone, the so-called Goldilocks zone, not too hot, not too cold, but just right around its host star. You need to know the properties of the host star in great detail. So you need to know its size, its mass, also how hot its surface is. That tells you how luminous the star is and how much energy it's therefore emitting. So the studies of planets go hand in hand with the studies of stars. Of course, studying stars, as I mentioned earlier, is of tremendous importance, of course, for informing our knowledge of the evolution of stars and populations of stars in the galaxy. But also as well, this goes hand in hand as well with informing our understanding of the planets that we're actually discovering. Now, the data that Kepler was recording, so measuring the brightness of stars, also enabled us to study the stars themselves by the small intrinsic variations in brightness that came about because of things happening on the surfaces of the stars. Be that, for example, small variations in the light levels due to regions of activity, like dark spots on the surface of the star, but also my particular area, changes in the brightness of the star resulting from sound waves or waves trapped inside the stars, giving rise to gentle oscillations. And this is the field of Astro seismology. So as the definition says here, and this really is in the Oxford English Dictionary, the study of the interior of stars by observation and analysis of oscillations at their surface. So stars make sound naturally in their interiors. The sound is trapped, even though a star doesn't have solid edges. it nevertheless acts as a cavity to trap the sound. You get standing waves set up then within the body of the star. And again, because the star is a big ball of gas, those compressions and rarefactions of those standing waves make the star oscillate. As the star breathes in, it gets hotter and brighter. And as it breathes out, it gets cooler and darker. So by measuring these periodic variations in brightness, we can actually learn about the internal properties of the star, because the variations in the light are telling us about the sound waves trapped inside, and the properties of those sound waves are affected by the properties of the material of the gas through which they're traveling. But also as well, not only can we build up a picture of what the inside of a star looks like, we can use the study of these oscillations to as well produce very precise and accurate measurements of the radii of these stars, also as well incredibly precise measurements of the mass, and also as well the ages of these stars. And those are the basic data that we need to be able to get a better understanding of the planets that we discover around those stars. So here's an example of the type of data we might get on a star. This is a planet hosting star called Kepler 66, and this is the spectrum of its oscillations. So stars don't just oscillate in one or two different modes or tones, they do so in many different overtones. So just in the same way that a musical instrument will resonate not just at one note, but in several overtones or harmonics, the star does the same. So when we observe the brightness variations of the star, we're not just seeing the result of one oscillation, we're seeing the composite effect of many oscillations. And if we look at do a frequency analysis of those brightness variations as a function of time, we can get something that looks like this, that's showing here on the vertical axis, if you like, the strength of the signal, and the horizontal axis is showing the signal strength at different frequencies. And you can see this characteristic comb-like pattern, just like the pattern we'd see from a musical instrument, showing all the natural intrinsic overtones of the star. And it's by measuring these overtones that we can build up this detailed picture of the interior of the star, and also measure with great detail its fundamental properties. So that's the field of astroseismology. Our involvement in Kepler in Birmingham was to lead work by a large international consortium called the Kepler Astroseismic Science Consortium that comprised about 500 scientists. And we were leading the large group of around about 150, 200 people that were studying sun-like stars, and also as well, a group as well that was characterizing the brightest planet hosting stars that were discovered, around which planets were discovered using astroseismology. Now, Kepler really, as I said, it's no understatement to say it really has revolutionized our ability to be able to study stars. But what Kepler did for the first 4 years of its mission was to study stars in a very tiny patch of the sky. It then went on to observe stars distributed around the ecliptic, but it wasn't observing the very, very brightest stars in the sky. So come the last decade, we were very excited to hear about and to get involved from very early on in this, a successor mission, the NASA TESS mission. So TESS is an acronym, the Transiting Exoplanet Survey Satellite. And we got involved from very early on in terms of actually setting up the TESS Astroseismic Science Consortium, and also again leading those parts of the consortium involving many scientists studying sun-like stars, and also as well the planet hosting stars. Now, what TESS was designed to do, which Kepler did not, was first of all to observe the very, very brightest stars in the sky, to as well look to, just like Kepler, look for brightness variations due to the presence of planets, but also as well to use those brightness variations to study the stars themselves. But also as well, unlike Kepler, which at any one time was only observing small patches of the sky, TESS was designed to observe a much larger fraction of the sky at any one time, as we'll go on to see, and also over the course of a 2-year mission to basically survey all of the brightest stars right across almost the entire night sky. Now, Kepler as well, one of the difference was in terms of the size of the satellite. Kepler was about the size of a bus, and you can see here TESS is much, much smaller. Now, TESS makes its observations through via the 4 cameras that you can see here. And you can see that the alignment of the cameras is such that they are stacked, so that at any one time, each of these cameras is observing a slightly different patch of the sky, and basically measuring the brightness of all of the objects, be they stars or maybe solar system objects, like planets or maybe comets, that fall within the field of view of each of the cameras. So this image here shows how that works. So the little figure at the center of the screen here, that's showing a little graphic, tiny graphic of the TESS satellite itself. And then if we look at this patch of the sky here, each of the 4 cameras has a field of view that's essentially a little sort of square on the sky. And then at any one time, the cameras are oriented so that they each observe a patch that basically maps out a sector on the sky that looks like this. If you like, a little bit like a strip from half of a Terry's chocolate orange. And what happens is that the satellite will basically stare at that fixed field of view for around about a month. So you're observing continuously the brightness of any objects that fall within these fields of view of the cameras for about a month. Then what happens is that the satellite rotates round and observes the next strip of sky. And then after observing that strip for a month, it then rotates round and observes the next strip, and so on. So that over the course of about a year, you've basically mapped out one hemisphere. The satellite then flips over and observes the other hemisphere. So over the course of approximately 2 years, you've basically mapped the brightness of all the stars in the sky, pretty much the entire sky. The coverage isn't complete. TESS was designed deliberately not to observe stars in the ecliptic. And as you can see here implied by this image, there are a few small gaps, but nevertheless, you're observing pretty much all of the bright stuff right across the sky. So here's another image here representing again the observing strategy. So again here you can see in this left-hand image here how each of the 4 cameras is observing a small patch of sky which combines to form a strip that's observed across any one month. And again, as you move on in the next month, you observe the next strip and so on. So that after 13 of the sectors, each sector actually lasts about 27 days, you've mapped essentially most of an entire hemisphere. Now, the closer you get to the ecliptic poles, so this is the ecliptic here, okay, and the orientation is such that you've got the ecliptic north pole pointing upwards, the ecliptic south pole pointing downwards. You can see here that there are going to be regions as you get closer to the poles, which are observed possibly in 2 or even more of these different observing sectors. The image on the right-hand side here shows the coverage of that. So you can see that the way things are oriented, stars actually close to the poles essentially get observed for the entire year. So it's actually 351 days. And then stars that are close to the ecliptic plane here, so for example, stars that are observed here by this camera, the camera that's observing closest to the ecliptic, are going to be ones that only ever fall within the field of view of that camera at that time, and they only ever get 27 days of data. The image on the right-hand side here as well shows the regions that were not covered during the so-called nominal mission. So these little patches here, and also as well the region close to the ecliptic. That was a deliberate choice because Kepler actually observed many regions of the ecliptic during its nominal mission. So TESS's nominal mission, designed to last 2 years, essentially doing a 1-year survey of each celestial hemisphere. Things actually started off like this. So it actually did the southern celestial hemisphere during its first year of operations, and then flipped over to do the northern celestial hemisphere. And those observations were completed, actually, this nominal mission was completed earlier this year. So that was the observing strategy, again, basically providing these exquisite measurements of the brightness of objects falling within the field of view. The primary goal being the observation of the brightest stars in the sky, but again, just picking up any other objects that would fall within the field of view, be they solar system objects or distant galaxies as well. So we wind back time then to just over 2 years ago, well, a bit more than 2 years ago now, to April 2018, and the launch of TESS at Cape Canaveral. I was very lucky to be one of the people, because of my involvement in the preparations for the mission, to be invited to the launch, which was fantastic. Still definitely my favorite ever work trip. And here's an image here of the top of the Falcon 9 rocket on which TESS was launched. So you can see here the so-called fairing. So this is the part of the rocket that protects the satellite during the phase of the launch when it's going through the Earth's lower atmosphere. Just again to reiterate size scale here, remember we saw how TESS isn't a very, very big satellite, and that sort of reinforces the point. You had this tiny, tiny satellite about the size of a fridge freezer right at the bottom of the fairings there. So that was the mission all set up, ready to go at the top of its Falcon 9 rocket at Cape Canaveral. Here are a few gratuitous pictures of me at Canaveral at the site where we were at the, in inverted commas, a VIP site that we were lucky enough to be at for the launch. So this overlooked, you see the top image there, this actually looked across the water at one of the lakes, or I guess they're lagoons at Cape Canaveral, looking onto the launch site that was just a few miles away. And initially, actually, we were there for several days. The first launch attempt, which happened a couple of days prior to the final successful launch that we're seeing here, the first attempt was actually scrubbed just as we were actually on our way on the buses out to the site to actually watch the launch itself. But we were lucky enough that we booked our flight such that we were able to hang on. We just had a insurance of about a day, so we were quite lucky that we were there actually for the actual launch that happened on April the 18th. And here's a nice image of that. This, of course, is not a picture taken by me. Here's a picture taken by me, okay? So this gives you an idea of the launch. So I'm not the world's greatest photographer. Here's a couple more attempts made by me to show the launch. So it's fantastic actually being there. Obviously quite nervous because we've been obviously involved in a lot of the preparations for the mission in terms of setting up, helping to set up this consortium, planning all the analysis we were going to do with the data. So a real relief that the launch went off without a hitch. Also a fantastic experience to see a real launch in the flesh. So I told many people who've asked about what it was like, the most striking thing was just how bright the plume of the rocket was. Also the noise as well, but the brightness of the plume of the rocket was the most striking thing. So that put TESS into orbit. It took a few weeks before it actually got into its science orbit. But once there, it was able to take its first light image, and this is the image here. So this really gives an impression here of the exquisite detail and the rich information content in these images. So if we look at the center of this slide here, so each of these squares here, the 1, 2, 3, and 4, is showing a snapshot taken by each of the 4 cameras at this particular time. And then you can see in a bit more detail then at the edges the rich content of these images here, showing a whole variety of different types of objects, of course dominated by the presence of stars. So it's from these basic images that we're able to extract light curves of the stars from analyzing the brightness variation over the course of the month or even longer that stars are observed, capturing variations in the brightness of the light of these individual objects over time that produces a light curve. And it's from those intrinsic variations that we can learn about the intrinsic properties, characteristics, and parameters of the objects that we're actually observing. So one of the first things that we had to do actually prior to the launch was actually deciding which targets were actually going to be observed at the higher cadence that TESS had. So this is observing the brightness of stars on a 2-minute cadence. And we need that rapid cadence to be able to follow the intrinsic brightness variations that result from oscillations in sun-like stars. And they have dominant periods of the order of several minutes. So you need to be able to capture those variations. Hence, we need to observe them in this mode of operation where the brightness is recorded every 2 minutes. So one of the big jobs that we had prior to launch was actually deciding which targets would be observed for astroseismology. And one of the things here in Birmingham that we did was actually leading the work on deciding which of the targets, which of the sun-like or solar-type targets would be observed. And that was selecting out around about 20,000 stars that would go then on the target list and be observed by TESS during the nominal mission. So here's an example of some of the sort of data that we got in some of the, I picked out just a couple of examples here from early publications that we produced. Here's the oscillation spectrum of a naked eye star called New Indy. So again, one of the things that TESS gave us that Kepler didn't was the ability to observe the brightness variations of the very brightest stars in the sky, stars we can observe with the naked eye. So here's the oscillation spectrum of this star. You can see here from the title of the slide, this is talking about age dating a collision or a merger that the Milky Way underwent using data on just this one individual star. So how does that work? So from this oscillation spectrum, and also from other information that we know about the star, we knew already from the other observations of this star that it was a very old star. It's been around in the galaxy for a very long time. And from these data, from measuring the frequencies of all the different components of oscillation we can see here, we were able to place very, very tight constraints on the age of this star. Also, as well, from other information on this star as well, we could pin down the fact that this was a star which was born within our galaxy. And it was not a star that ended up being in our galaxy because of the collision of another galaxy. And there have been several collisions the Milky Way has undergone throughout its history. One that has garnered particular interest over the last sort of couple of years has been the collision of a galaxy called Gaia Enceladus. The fact that this large galaxy, which had a mass that was about a quarter of the mass of the Milky Way, the fact this galaxy had collided with the Milky Way and details of that collision really came to light as a result of the wealth of data we got from the European Space Agency Gaia mission. So very early in its history, the Milky Way underwent this collision. And as a result of this collision and other collisions have helped to shape the evolution and also as well the content of stars within the Milky Way, leading to the galaxy that we actually see now. But one thing that we know from looking at this particular star, New Indy, we know it was born within the galaxy, so it didn't come in with Gaia Enceladus, but we know that its motion within the galaxy was actually affected by this impact. And as a result of that, it enabled us to place constraints on when this merger happened. So that's a really nice example of showing how data on just one very bright star can tell you something about the overall history of the galaxy. But one of the other things, of course, we've been doing with TESS is using astroseismology of planet-hosting stars to parameterize and constrain the properties of the host star, and hence, therefore, to place constraints on the planets that have been discovered. So this was actually the first system with TESS, where TESS had discovered a planet, and the star also was bright enough to enable us to do the astroseismology. So on the left-hand side, we've got the overtone spectrum of the star. We used that then to measure the properties of the star in great detail. On the right-hand side, we've got the transit curve produced by the dimming of the planet as it orbits the star. That's the TESS data. With this star as well, with ground-based telescopes, we were able to as well observe or detect the planet, the presence of the planet as well, from it pulling or tugging on the star, giving rise to variations in the velocity of the star. And that gives rise to this radial velocity light curve or Doppler wobble signal on the bottom right-hand side. And by combining all these data, that enabled us to actually provide a measurement of the absolute size of the planet from the transit data, combined with the absolute size of the star. And also we could as well measure the absolute mass of the planet from the Doppler wobble data, combined with the mass of the planet inferred from the analysis of the star that used the Astro seismology. And we're now starting to do this as well on more systems. One other thing that we were involved in as well last year was actually preparing the case to NASA to actually get the mission extended. So one of the things I helped to do was to actually coordinate the input that the Astro seismology community provided to the so-called NASA senior review process. The mission was extended. It's been a great success so far. And as of now, it's now into its extended mission phase. TESS will have enough fuel on board to, in principle, be able to continue its mission for maybe a decade or more. So there are real prospects here for TESS to be able to continue on taking its data, fingers crossed, for many, many more years to come. And there will be exciting opportunities in the future to actually come up with new modes of observing and have TESS focus on different parts of the sky for detecting and collecting different types of data. So the future is very, very bright with TESS. I think TESS is going to be carrying on collecting data, possibly all the way through to the end of my research career. And with that, I will end. I hope I've given you a bit of a feel for the TESS mission and all of the exciting results that it's already produced and it will go on producing over the coming few years. Thank you.
Okay, hello everybody and welcome to the Q&A session for AstroSoc's 9th quarantine talk. We are absolutely delighted to have Prof Bill Chaplin with us today, who has just given you that talk. It was absolutely wonderful and we are really excited to hopefully have any questions that you might have from that talk and be able to present them to Professor Chaplin today here with us.
Thank you very much.
So at the moment, it is looking like we don't have any current questions on the YouTube chat. Please do post any questions you have there, and you are also more than welcome to come and join us on this Zoom call. We would be delighted to have you join us. I guess for the time being, we'll start off with any questions that the committee might have. So I'll start off with one that I have myself, which is, could you possibly explain to us how the telescope is able to stare at a fixed patch of sky? Obviously, the Earth is rotating around the sun, but you kind of highlighted how it looks at one fixed patch for a certain number of days. How does this work?
So missions like TESS or also Kepler that I mentioned as well. So they use things called reaction wheels. So basically using angular momentum to basically stabilize the spacecraft. So you have several of these wheels, a bit like a gyroscope, and you have 3 of them. Basically is what you need is for the 3 dimensions, and that is able to, by having these sort of effectively these spinning gyroscopes, they're able to keep the spacecraft stable in 3 dimensions to ridiculously silly levels. Kepler was actually launched with 4 of them, so with 1 backup, and sadly 2 of them failed. So which was quite unusual for a spacecraft, and so that actually ended Kepler's nominal mission after 3.5 years instead of the original intended 8. But then the people who actually built the spacecraft and also NASA thanks to their ingenuity, they figured out a way to actually run the spacecraft and do a reasonable job with just 2 of these reaction wheels. And so Kepler carried on as something called K2 for, well, all the way up until the middle of last year. So the quality of the data weren't quite as good, but they weren't actually too bad. So yeah, so fortunately there are no problems at the moment with TESS, and it actually has enough fuel to last maybe for another 20 years or more. So it may just be reliant on basically funding, getting a recurrent budget from NASA to carry on, rather than any technological issues.
Awesome. I guess kind of as a short follow-up question before I go to the question on the chat, with the TESS mission being extended, is the hope to get just a larger amount of data on the same stars? Is it a hope to switch the targets, or what kind of thing is the extension designed to do?
That's a good question. So the first extension is pretty much, though not exactly, a repeat of the nominal mission. So it's going to go back and actually look at exactly pretty much the same patches of sky, apart from one stretch when it will look at stars in the ecliptic plane, which it didn't during the normal mission. So the idea really is just to add another, and effectively another year of data on each the northern and southern hemispheres. And this will add first of all, it's a good strategy for increasing the yield of detected exoplanets around the stars, but also as well for us studying the stars themselves. It will enable us to revisit the same stars, effectively a year or more later. And so we'll be able to look for changes in the stars, but also provide a longer time base on the stars as well for studying their interiors. What happens, so the way that NASA works is they do a thing called the senior review, which reviews all of the active missions. And they do this on a 3-year timescale. So it's like a rolling thing. So the review now that was approved last year gave an additional 3 years of funding. But probably in about a year's time, we'll probably be starting to think about what to do for the subsequent role. And I think it's very likely as time goes on, and assuming that the mission still gets funded, that the scenario for which bits of the sky are looked at will probably change down the line. But for the moment, it's just effectively more of the same, which sounds a bit boring, doesn't it? But in this case, it's a good thing.
Yeah. Okay. No, that definitely makes sense. Thank you. I'm going to go to the question that we've had on the YouTube chat, and that is saying that in the slide showing targets for astroseismology, how is it that stars are shown in the ecliptic?
So originally what we did there is to just select everything, and then once we knew exactly where the spacecraft was going to be pointing, then that would remove the ones that it was not possible to observe. Also as well, I mean, aside from the fact that the decision was made eventually not to observe stars in the ecliptic, also as well, there are certain patches of the sky where because of the way that the Terry's chocolate orange sectors overlap, there are some regions of the sky that effectively don't fall on silicon. So what that means is that those little small patches don't fall on a detector. And again, it's quite hard to predict where they will actually fall, unless you know exactly where the observing sequence starts once the mission starts collecting data. So again, we just didn't worry about that at the stage when we were selecting the targets. We just selected everything. And then once the spacecraft started observations and we knew where it was pointing, anything that didn't fall on silicon just didn't get observed. So it kind of took care of itself.
Thank you very much. I'm hoping that answers the question well. I'm going to go for one more question from myself before I kind of let some of the rest of the committee jump in. And that is, obviously, you've mentioned the fact that Kepler was observing some of the dimmer stars and that TESS is observing some of the brighter stars. Was there any particular reason that these two segments, or subclasses, I guess is probably the more accurate word, of stars were chosen?
So Kepler deliberately went for slightly fainter stars, just simply because there are more of them. So there was some there are always limitations when you have these big CCD detectors around effectively their dynamic range. So the range of apparent brightnesses of stars that you can actually observe with those detectors, and of course then that maps then to how far away the stars are. Of course, as you go to fainter and fainter stars as they appear, you're tending to then go to greater and greater distances where there are more stars. So there's a bit of a trade-off of where you want your sweet spot to be. Kepler was very much a statistical mission. What it really wanted to do was to be able to observe enough stars to be able to generate really, really good statistics on estimating, for example, how common are Earth-like, potentially habitable Earth-like planets orbiting other sun-like stars. And that's quite a tricky question to answer. So you need to observe lots and lots of stars to get that answer. So Kepler deliberately targeted stars slightly further away, fainter stars, again, just because there are more of them. TESS, on the other hand, was designed to, because it was much smaller, so the light collecting area is much smaller. So what that means then is to get the same quality of data, you have to be observing a much brighter star with TESS, than with Kepler. So to get the same noise levels, a star has to be around about 4.5 magnitudes brighter when observed with TESS than with Kepler. So that anyway sort of biases you towards brighter stuff. And also as well, the decision was made, to be able to pitch the dynamic range so you could do the brightest stuff in the sky, which is kind of sexier because, people know those stars, they're the best studied through other means. So it's a bit of a sort of a bit of a trade-off. Also as well, we always knew that TESS would give us really good statistics because unlike Kepler, which stared at this small patch of the sky, TESS was going to, and has done, is observe stars right across the sky. So that generates that takes care of generating the big numbers, and it means you can target the brighter stuff, basically.
That is brilliant. Yeah, no, that again all makes perfect sense. So thank you very much. I'm hoping that there might be a few other questions.
Yes, while we wait for some more questions from the chat, I can ask a couple more of my own.
Fire away.
About 4 or 5 days ago, I was reading an article on space.com about the detection of a Jupiter-sized exoplanet around the white dwarf star WD 1856. And they particularly highlighted that this was a very unique discovery in the sense that this planet was intact, especially after the process of the star being converted into its white dwarf form. And I was just wondering, what's your opinion on what could have caused the planet to move inwards, and how did it survive this violent creation process of the white dwarf? And how could we use TESS and similar missions to determine the cause of this?
It's a very good question. So I think, it is maybe a little bit surprising that this planet did survive the evolution. So the crucial thing here is that in going from, if we think about the future of the sun will, in a few billion years' time, well, still about 5 billion years away, but it will swell up to become a red giant. And so during that process, the Earth will be engulfed as the sun swells up to become, many, many more times bigger than it is at the moment. And so there is an interesting question around, whether or not planets can actually survive that period of, enlargement as the star evolves, the process of engulfment, the fact there are other subtle things that happen as well to do with angular momentum conservation and other stuff where you'd expect the orbits of the planets to change as well. So there has been, certainly with Kepler actually, that generated a lot of interest in actually trying to find planets around more evolved stars. And there are several large international programs or consortia that are using TESS data now to try and get a handle for what's the population of planets around more evolved stars. I think naturally the sort of focus on trying to understand, how many planets are there out there has been very much focusing on stars like the sun. but thanks to Kepler and also lots of ground-based surveys that have discovered some more evolved planet hosts, there is now definitely a concerted effort to try and understand what happens, in these more evolved systems, and do planets survive? And a lot of that depends a little bit as well on the mass of the star. The mass of the star as well determines different details of the process the star goes through as it evolves to become a red giant. So it expands, gets really light and fluffy at the edges, and then it very easily loses its envelope, and effectively what's left over, the core of the star, contracts down to form the white dwarf. So I suspect that we will be able to better answer those questions in a few years' time once we get more detections with TESS. Now people have found this one example around this white dwarf. I think now people will know what sort of signature to look for, and for sure people will be looking around at the white dwarfs as well, I think. So, yeah.
As a short follow-up to the question I just asked before I head on to the next question on the chat, how do we know for sure that this planet was in fact a planet of the white dwarf star? In fact, like, how do we know that it wasn't, for instance, a stray planet or an interstellar planet that was captured by the white dwarf after it turned into a white dwarf?
Yeah. I guess for the latter, I mean, there are, people have searched for what are called free-floating planets. So planets that for whatever reason have been, dynamically ejected from their stellar systems and from their star. I think that the chances of, if you actually sort of work out, what the probabilities of stars within a galaxy actually dynamically interacting with one another, unless that they were actually born as part of a binary system, so that they share that common origin, it's a very, very low probability. So, the probability just says, yeah, it's going to have been a planet that's associated with that particular star.
Thank you very much. The next question from the YouTube chat asked the following. So it says, were any other projects launched at the same time as TESS, as it looks like it didn't need all the space available?
Oh, yeah, okay. So the answer is no. So I think the way that, so what NASA did is they actually signed this contract with SpaceX to launch TESS, but did so with it being, an exclusive single ride mission. So it's not always the case, as you probably know, with SpaceX launches. Sometimes they do launch more than one payload at the same time. But here the requirements around the orbit that the TESS went into. So it's quite an unusual orbit that I think was dreamt up by some very clever person at MIT, which involves a resonance with the orbit of the moon around the Earth. So there are, it's quite a unique orbit. And so that meant that there were quite specific requirements around what the second stage had to do to, once it had got into its initial orbit around the Earth, what was then required to put the spacecraft into its operational orbit. So yeah, even though there's a huge amount of space, it's actually not that big a spacecraft. It was launched on its own.
Thank you very much.
We've got another particularly interesting question that has come up on the YouTube chat, one that I think you'll be very well placed to answer. And that is, do continuous ground-based observations of our sun continue to have advantages with respect to stellar modeling?
Oh, that's a good question. So, yeah, so I should mention, we in Birmingham, we've got a network of telescopes that we run that make these sort of seismic observations of the sun, and have been doing that since as a global network of observatories since the early 1990s. I guess there are differences between what you do maybe with a space-based mission and a ground-based mission. First of all, space-based missions tend to be rather more expensive. They require a lot more forward planning. So they're, and you tend to have a huge, great big international consortium behind it in order to get one of these things selected and developed. But obviously it comes with the advantages of, giving you, as we've had with Kepler and TESS, near continuous observations of the stars at very high cadence. So with both missions, we've been getting data back on a 1 or 2 minute cadence for, many months at a time on some stars. ground-based data, obviously you've got this challenge of the gaps in the data. So the kind of science we do, gaps are a bad thing. You want as near continuous coverage over years, if you can get that. So obviously then there's a challenge of having to run a network of telescopes, but it is cheaper, and also as well because it's all ground-based, provided you can travel, which we can't at the moment for obvious reasons, but provided you can travel under normal circumstances, it means that you can, handle, I don't know, bits of equipment breaking, going wrong. Something goes wrong on a satellite. Usually, it's very, very difficult to work around that. But with something ground-based, you can. And the other thing you can do, of course, is that you can innovate and you can evolve your instrumentation. And that's something that we've done with our network. So over time, even though the type of observations we're making are very similar, to 30 years ago, parts of the instrumentation have been completely revamped and changed. So there's that ability as well. So the two, I guess, kind of complement one another. I mean, usually with ground-based telescopes, we use those in combination with the astroseismic data from Kepler and TESS to provide other information. For example, information on measuring the surface temperatures and the compositions of the stars that we can do with big ground-based, what are called spectrographs, that make Doppler velocity observations of the star. And those spectrographs tend to be very, very heavy, so you don't get very many that are launched into space. Again, because stuff that's heavy is more expensive to launch. So it's kind of trade-offs, I guess, in terms of what one wants to do.
I'm hoping that answers the question, but I guess just as a slight follow-up, kind of in terms of actual using the data to develop our stellar models, are we still actively trying to model the evolution of the sun and refine that model, or is that kind of fairly well fixed now, and are we then more focusing on, for instance, giant stars and dwarf stars?
That's a good question. So for the sun, no, there's still a lot we don't understand. I think the quality of the what the conclusions we can now draw on what the inside of the sun looks like, whilst the models generally do, I mean, they do a pretty good job. I mean, for example, if you compare effectively with the oscillations, we're measuring the sound speed through the star. So if you compare the measured run of sound speed through the star with the best models, the agreement is good at the level of 1% or better. But because we can measure the sound speed to such a ridiculous precision, even though those differences are at a level of 1% or less, they're still significant. So there are things that we don't understand about processes in the star that relate to the way the material is mixed around, the impact that magnetic fields have. Anytime you have magnetic fields in a modeling problem, it's a real nightmare. So that complicates things. But also as well, we don't yet properly understand how rapidly the deeper parts of the core rotate. So we can measure the speed of rotation of the sun down to the outer edge of its core, but any further than that, and we really are not sure. So, and there are aspects as well about the profile that we see of the sun's rotation versus what was expected prior to making those measurements. The two didn't agree very well at all. So there's lots of things we do understand about stars, but clearly lots of things that we don't, and there are known unknowns and unknown unknowns. So yeah, I think it really, having these data has really revolutionized our ability to attempt to properly answer these questions, which maybe before was a lot more challenging.
Excellent, thank you.
I've got one more question on my end, if we've got enough time to continue.
Yep.
Perfect. During the span of your research career in astroseismology, what has been the most exciting research or observation or discovery, and what advice would you have for aspiring astrophysics students?
Oh, crikey. I think for me, what's the most exciting thing? Probably, I think when we, the first data that we got from Kepler, first time we saw that, I was one of a few people who was sent initially some data on just 3 of the many thousands of stars that were observed. And just then the realization that the quality was going to be good enough to do all these other amazing things that we had planned. So I think that's probably the one thing I think that would stick in my mind. I think in terms of advice, ooh, crikey. I guess thinking about, I mean, for me personally, I certainly what I do studying stars wasn't originally what I was intending to do. So originally my interest really was finding planets around other stars. And I kind of got, so I did that for my PhD, but then the opportunity arose to actually use some of those similar sort of data analysis techniques and observations to kind of switch fields to actually studying the stars. And this was actually a switch to actually studying the sun. So I guess from that perspective, I would say that, you know, obviously, if you're thinking about a career in astronomy, you will certainly have things that you are interested in, you know, areas that you're definitely interested in. But I don't know, research moves very, very quickly, and it's very hard to predict, I think, what you're going to be doing 5 years down the line. Is just the nature of research. So I think my advice would probably be, you know, if you've got an area you want to work in, still be open-minded, and when opportunities come along, you know, grab them with both hands. Don't be afraid to maybe switch direction if a really exciting opportunity arises. And I kind of, that's what happened to me. I just kind of went with the flow and changed tack slightly, and it worked out in the end. So yeah.
Thank you very, very much.
Thank you.
I think that looks like that is all the questions. From everything you've said, it sounds like both the fields of exoplanetary science and astroseismology are absolutely fascinating, and still with a lot of work yet to be done on them. So are great areas to go into. I know my personal interest is in exoplanet science, but obviously I have worked alongside you last year on this astroseismology stuff, and it was really, really amazing. On behalf of AstroSoc, I'd like to say thank you once again for a brilliant talk and some amazing answers to the questions that we've had. It's been a pleasure to have you along.
Thank you, and thank you very much for asking me again. It's been a pleasure to give the talk and answer the questions. Thank you.
Thank you very much.
Well, it looks like, yes, that is kind of us wrapping up. I will very quickly say that we have our final talk next week, same time, so at 3 p.m. on Monday. And this is going to be from